Welcome back to another video. This video is on periodic trends, and it's a comprehensive review that is similar in style and difficulty to what you'll be tested on. So, question 1, arrange the following period 2 atoms in order of decreasing atomic radius from largest to smallest. So with this whole entire unit, it's really helpful if you have the formula sheet right next to you because you're going to be relying on that a lot. So what I like to do is go to the formula sheet and first highlight the elements that we're focusing on. So in this case, we have lithium, beryllium, carbon, nitrogen, and fluorine, and it's asking us to figure out the order of atomic radius. So as we learned, atomic radius increases down a group and decreases across a period. So that means as we move from left to right, the atomic radius will decrease, and this is because the element on the right will have more protons and therefore a higher effective nuclear charge, which then pulls the electrons in more. So we'll basically just write it in the order that we see it here. So lithium will be greater than beryllium, which is greater than carbon, nitrogen, and then fluorine is the smallest. So on this side, we have the lowest effective nuclear charge because it has the least amount of protons. And here we have the highest effective nuclear charge because it has the most protons. And what happens is with a higher number of protons, the electrons are pulled in more. And then this results in the smaller atomic radius. So the answer is A. Next, question 2, a period 3 element has the following successive ionization energies. So this question, I would say, is likely to show up on the test. And with these types of questions, you don't really care about the values. What you're mainly looking at is wherever you see a very big jump in the ionization energies. So we'll look through this table that they give us, and I see that there's an unusually large jump from the third ionization energy to the fourth. And basically what this indicates is the jump means that it's losing an electron shell. And it goes down a period. So what causes this really big jump in the ionization energy is it now has the same number of electrons, or it's isoelectronic with the noble gas, and that's what makes it so difficult to remove that electron because it has a full shell now. So because it's between the third and the fourth, we can go back to our periodic table. So this fourth ionization energy means that it's at the noble gas. So it's fourth, and it's a period 3 element. So if it's a period 3 element, then the next noble gas from losing electrons will be neon. So the fourth electron that it loses is neon. So that means we count backwards. So it will be 1, 2, 3, 4, and we land on aluminum. So therefore, our answer is aluminum. Okay, so I was reviewing the video and I realized that that explanation maybe wasn't the most clear. So this is a much clearer way of putting it instead of just 1, 2, 3, 4. So the fourth ionization energy was neon. So this is IE4. And then IE3 would have been sodium. IE2 would have been magnesium. And then IE1 would have been aluminum. So it started at aluminum, so that's how we know this is correct. Question 3, which of the following rankings of atomic or ionic size is false? So let's go through this individually. The first one is that O2 minus is greater than O. This is true because anions are always greater than the neutral atom. And the reason that this happens is because there is electron repulsion in the electron cloud. which forces the electrons to space out a little bit more, which will make the size larger. Next, K plus is greater than Ca2 plus. So let's look onto our periodic table. Ca is here, K is here. So if it's K plus and Ca2 plus, then they have the same number of electrons as argon would have, so that they're isoelectronic. So what's going to determine what's bigger than the other is the effective nuclear charge. Calcium has more protons than potassium, so it has a higher effective nuclear charge. So same number of electrons, but calcium has a higher effective nuclear charge, so its electrons are pulled in more, making it smaller than potassium. So this is also true. Next, Mj2 plus is greater than Na plus. So Na is here and Mg is over here. They have the same number of electrons again, so this is kind of the same process as the one above, but it's saying magnesium is greater than sodium. This is not true because magnesium has more protons, it has a higher effective nuclear charge, and electrons are pulled in closer, so it should actually be smaller than sodium. And then the final one, let's just confirm to see if this is true. Chlorine, argon, and potassium, which are here. So these again all have the same number of electrons. So what we're looking at is the number of protons they have, and potassium has the highest effective nuclear charge and chlorine has the lowest. So therefore, it would be the smallest size. So this is C. Next, the period 2 elements from left to right are this. Rank the following atoms in order of increasing first ionization energy. So once again, I'm going to highlight which ones we're working with. So we have lithium, beryllium, boron, oxygen, and nitrogen. So with first ionization energy, the pattern is this way. It increases across the period and decreases down a group. So the basic trend is that we would expect the first ionization energy to increase this way. But with ionization energy and electron affinity, there are two small exceptions to this, and that is with nitrogen and beryllium, and it has to do with the subshells. So basically, with beryllium, it has an S shell, and it has 2 electrons. And with nitrogen, it has a half-filled P subshell. And what occurs is nitrogen will actually have a higher first ionization energy than oxygen, even though it's to the left of oxygen, because it has that half-completed subshell, and it really does not want to lose it because it's more stable this way. So what happens is nitrogen and oxygen just do a little switch. And it's the same thing with beryllium and boron. Beryllium has this completely filled S subshell, while boron has a filled S and just 1 electron in the P subshell, so it's easier for it to lose that electron and have just that stable S subshell. So boron and beryllium will also do a switch. So essentially follow the pattern from left to right, but then just switch the 2 that need to be switched. So therefore, lithium will have the smallest, and then it will be boron, then beryllium, then oxygen, and then nitrogen, which is A. Question 5, 4 spheres labeled A, B, C, D represent Na, Na plus, Cl, and Cl minus in some order smallest to largest. Which assignment is correct? So what this question is telling us is we have these spheres that get bigger, and we need to assign each of these spheres to the 4 species. So how we'll do that is we know that the neutral atom is greater than its cation, and the anion is greater than the neutral atom. And then let's compare Na and Cl. So Cl and Na are in the same period, but chlorine has a greater effective nuclear charge. Therefore, electrons are pulled in and it has a smaller radius. So we know that sodium is greater than chlorine. So with Na+, it loses an electron and it's now isoelectronic with neon. So it's the one that loses a shell, so we would expect that to be the smallest. And then between Na and Cl, Cl is smaller. And then it will be sodium, and then Cl minus, the anion, would be the largest. And I just want to point out that in our lecture notes, it states that the neutral group 1 is basically equivalent to the size of a group 17 cation or anion. And then a group 1 cation is similar in size to the group 17 neutral atom. So what this means is Na plus is a group 1 cation, and it is similar in size to the group 17 neutral atom, which is chlorine. So technically these two are interchangeable according to the McMaster notes. Different sources will say different things, but this is what's in the lecture slides. And then a neutral group 1, which is sodium, is similar to a group 17 anion, which is chlorine. So these two are also interchangeable. So technically, according to McMaster's notes, B and D are acceptable answers as long as you kind of keep this divide between the two. Okay, question 6. Which of the following statements about electron affinity is correct? Letter A, noble gases have the most negative electron affinity values because they strongly attract electrons. This is not true because noble gases have a full shell. When they have a full shell, they're happy and they don't want any more electrons. So this is not true. B, group 2 elements have more negative electron affinity values than group 1 elements in the same period due to a higher effective nuclear charge. This is not true because although we do have a higher effective nuclear charge, we talked about how it has a filled S subshell where there's an exception. And basically a more negative electron affinity value means that they want to gain an electron more. But group 2 elements don't want it more than group 1 elements because they already have that filled S subshell, while group 1 elements only have one and they really want another one to complete it. Cn has a less negative electron affinity value than C because N has a half-filled 2p subshell, which is especially stable. This is true. So if you look at nitrogen and carbon, nitrogen's here, carbon's here. Nitrogen has a half-filled p subshell, while carbon only has 2. And then this will make nitrogen have a less negative electron affinity, because once again, having a more negative electron affinity means that they want another electron, but nitrogen wants it less than carbon because it has the half-filled p subshell. So this is the answer. Let's look at D. The electron affinity always becomes more negative going down a group. This is not true, and it becomes more positive down a group. Or let's say it becomes more positive. And this is because there is more shielding by the inner shells, because when we go down a group, we gain more shells. So there's more shielding, and therefore less energy released. Okay, question 7. Which statement correctly explains why atomic radius increases down a group? A. The effective nuclear charge decreases significantly down a group, so electrons are held less tightly. This is not true. Effective nuclear charge actually remains relatively consistent down a group. And this is because, yes, they are gaining more protons, so the nuclear charge increases, but shielding also increases by the inner electrons. So the effective nuclear charge will stay relatively consistent because these two factors kind of balance each other out. So B, electrons are added to higher principal quantum number shells that are on average farther from the nucleus. This is true. Basically, the main reason why atomic radius increases is because they're adding another shell, and that adds to the atomic radius. And then let's look at why C and D are incorrect. So C is the number of core electrons decreases down a group, reducing shielding. This is the opposite of what we said in our explanation for A. The core electrons will increase down a group, and then there's more shielding. And then D, the nuclear charge Z decreases down a group. Nuclear charge increases down a group because there are more protons. And this is not the same as effective nuclear charge. This is just nuclear charge, which is the number of protons. So C and D are both incorrect. Question 8, a period 3 element has the following successive ionization energies. This is similar to what we were doing earlier. So once again, we have to look at between which two ionization energies do we have the biggest jump. And I think it's between 1 and 2. We're going from 400 to 4,000. And I know that there are big jumps over here as well, between like 6 and 7 and 4 and 5. But with proportions, this is the largest jump because we're gaining like 4,000 here, but only 2,000 in the next one, and then 3,000. And so over here, it like increases in a linear fashion, but with 1 and 2, it's like much bigger, and then it gets smaller and then increases here. So this is where the pattern kind of breaks. So it's between the first one and the second one. So what element is this? This means that the second ionization energy is the one where it's at the noble gas, and it's a period 3 element. So that means the noble gas is neon again. So if neon is the second one, then the first one is sodium. So it loses one easily, and then the second one is really high because it's at neon, which is the noble gas. So it's sodium. Question 9, consider period 3. Which of the following correctly explains why the ionization energy of phosphorus is greater than the ionization energy of sulfur? So A, S has a larger atomic radius than P, so its valence electrons are held less tightly. This is not true because sulfur is smaller than phosphorus because it has a higher effective nuclear charge, so it has a smaller radius. B, S has higher effective nuclear charge than P, so removing an electron requires less energy. Yes, sulfur does have a higher ZF than P, but this makes it require more energy to remove an electron. So this is also incorrect. A higher ZF means it's harder to lose an electron. C, P has a half-filled 3p subshell, which is especially stable, making it harder to remove an electron from P than from S. So let's look over here. Phosphorus is in group 15, which is the spot for an exception. So here's the p subshell. 1, 2, 3. This is what phosphorus has. And then 1, 2, 3, 4. This is what sulfur has. So because the phosphorus one is exactly half filled, it's pretty stable this way, so it doesn't want to lose another one. Whereas for sulfur, it could lose another one and then become perfectly half filled. So this is the main reason why sulfur has a lower ionization energy than phosphorus. Yeah. So our answer is C. It's always to do with the half-filled subshells. And then let's look at D. S has more valence electrons than P, so electron-electron repulsion makes removal easier. So electron-electron repulsion is very weak, and it's not the main reason why it's easier to remove an electron. And this pales in comparison to the increase in effective nuclear charge from P to S. So this isn't really a valid argument because this extra electron is much weaker than the extra effective nuclear charge that S has. So then this is not the answer. Question 10, we have 4 spheres labeled W, X, Y, and Z. The smallest is W and the largest is Z. And which pair of reactions best matches the relative sizes shown? So let's first determine the order, like which one is which. So we know that the calcium cation is smaller than calcium, and then the sulfur anion is greater than sulfur. Between calcium and sulfur, which one is bigger? Calcium is here and sulfur is here, so obviously calcium is in a higher period, so it has an extra electron shell, so calcium is bigger than sulfur. So our order will look something like this. And this is an interesting debate where we don't really know, where like some sources say that the sulfur anion is actually greater than the calcium atom, but they wouldn't expect you to know that. So based off of the knowledge that we have, we know that calcium has an extra electron shell above all the other species, and sulfur, although it's an anion, it doesn't have that extra shell, so that's why I put it at Y and not Z. And then with the calcium cation and sulfur, these have the same like electron shell, but calcium has more protons, a higher effective nuclear charge, and that's why I put it as smaller than sulfur. So that was the logic behind like corresponding each one, and now I have to figure out what the reactions are. So the calcium cation If it gained 2 electrons, it will become calcium. So W plus 2 electrons will make Z. And if S plus 2 electrons equals S2 minus, then X plus 2 electrons is Y. So this matches D. Next, question 11. Which set of atoms or ions is arranged in the correct order of increasing size from smallest to largest? So these are the species we're looking at. It's all the same for each option. So let's go to our periodic table. We're looking at the aluminum cation, magnesium cation, and the sodium cation, neon, and then the fluorine anion. And these all have the same number of electrons, and they're all isoelectronic to the neon neutral atom. So 10 electrons each. So what is going to determine the order of the sizes is effective nuclear charge. Which one is the highest? It's aluminum. It has the most protons, and then fluorine has the smallest number of protons. So therefore, the smallest size will be aluminum, and the greatest size will be fluorine. And this matches option A. Last question. Arrange the following elements in order of increasing magnitude of electron affinity from least negative to most negative. So, as we said before, the more negative electron affinity is, the more badly it wants to gain another electron. So we are looking at magnesium, phosphorus, sodium, chlorine, and sulfur. So they're all in the same period again, and electron affinity follows this pattern. So as we go across the period, it should increase, but with electron affinity, we know that there is a few exceptions, and that is with group 15 again and group 2. So with magnesium, it doesn't really want to gain an extra electron that badly because it already has a completely full S subshell, whereas with sodium, it only has one, and it's one away from completing that S subshell, so it really wants another electron, and it wants it more badly than magnesium. So this is where the rule doesn't apply, and then these two do a little switch. And then with phosphorus again has the half-filled P subshell, and this actually doesn't really apply because we're not looking at silicon, but it would want it less badly than silicon would, so it would have a less negative electron affinity than silicon, but we're not really looking at that. So actually, on this side, we can just follow the rule as is. So our order will just be the order from left to right, except magnesium and neon do a little switch. So magnesium is the smallest, then sodium, then phosphorus, sulfur, and then chlorine. So the answer is A. So that was our last question. Thank you guys for watching this video, and good luck with your studying.